Hello students, in this lecture I am going to discuss about hardware software co-design and program modeling. So in the development approach of a traditional embedded system, at an early stage the partitioning of hardware and software is done and engineers from the software group take care of the software architecture development and implementation, whereas engineers from the hardware group are responsible for building the hardware required for the product. There is very less interaction between the two teams, that is the hardware and software teams, and the development happens either serially or in parallel. So once the hardware and software are ready, the integration is performed. But the increasing competition in the commercial market and for reducing the time to market, a novel approach for embedded system design is developed, in which hardware and software are co-developed instead of independently developing both. So during the co-design process, the product requirements obtained from the customer are converted into system level needs or processing requirements, and at this point it is not segregated as either hardware requirement or software requirement. Instead, it is specified as functional requirement. The architecture design follows the system design, and the partitioning of the system level processing requirements into hardware and software takes place during the architecture design phase. So, uh, I discussed initially it was hardware software partitioning, it was done at an early stage, but now we develop hardware and software we co-design the hardware and software. So the fundamental issues that have come across in hardware software co-design are, first is selecting the model. So it is hard to make a decision on which model should be followed in a particular system design. The reason being the objective varies with each phase. For example, at specification stage, only the functionality of the system is in focus and not the implementation information. So when the design moves to the implementation aspect, the information about the system component is revealed and the designer has to switch to a model capable of capturing the system structure. The designers switch between a variety of models from the requirement specification to the implementation aspect of the system design. Now second is selecting the architecture. So the architecture tells how a system is going to implement with respect to the number and types of different components and the interconnection among them. The controller, so these are, here I'm going to tell you about some commonly used architectures in system design, like controller architecture, data path architecture, complex instruction set computing. Then we have this reduced instruction set computing, finite state machine data path, very long instruction word parallel processing architecture, etc. So the controller architecture, it implements the finite state machine model using state register and two combinational circuits. The data path architecture is best suited for implementing the data flow graph model, where the output is generated as a result of a set of predefined computations on the input data. Then finite state machine data path architecture combines the controller architecture with data path architecture, and it implements a controller with data path. The controller generates the control input, whereas the data path processes the data. Then complex instruction set computing. The use of single complex instruction in place of multiple simple instructions greatly reduces the program memory access and program memory size requirement. However, it requires additional silicon for implementing microcode decoder for decoding the this complex instruction set computing instruction. On the other hand, reduced instruction set computing architecture uses instruction set representing the simple operation, and it requires the execution of multiple RISC instructions to perform a complex instruction. Next is very long instruction word architecture. It implements multiple functional units, that is ALUs, multipliers, etc. in the data path. Next is parallel processing architecture. So it implements multiple concurrent processing elements, and each processing element may associate a data path containing register and local memory. So single instruction multiple data and multiple instruction multiple data architecture are example of this parallel processing architecture. In this single instruction multiple data, a single instruction is executed in parallel with the help of processing elements, whereas the processing elements of multiple instruction multiple data architecture execute different instructions at a given point of time. Then the next issue is selecting the language. So a programming language, it captures a computational model and maps it into the architecture. So a model can be captured using multiple programming languages like C, C++, C hash, Java, etc. for software implementations, and languages like VHDL, System C, Verilog, etc. for hardware implementation. Next, I'm going to discuss about the computational models in embedded design. So the first is data flow graph or diagram model. So data flow graph or diagram model, you can see here this data flow graph model. It is a data driven model in which the program execution is determined by data. This model emphasizes on the data and operations on the data, which transform the input data to output data. So here data flow graph, it is a visual model in which the operation on the data is represented using a block, that is a circle, and data flow is represented using arrows. So an inward arrow to the process, as you can see, an inward arrow to the process, or you can say the circle that is representing the process on the data, it represents input data, and outward arrow from the process, it represents output data in data flow graph model. So the example, this is showing the example. One of the functions in our application contains computational requirement, that is x is equal to a plus b and y is equal to x minus c. So how this has been represented using this data flow graph model, that is x is equal to a plus b and y is equal to x plus c. So this operations are represented, plus minus operations are represented using this circle, and the data is represented using the arrows. Data yani means a, b, x, y, etc. So a plus b is equal to x, and then x minus c is equal to y. So this is x minus c. Y is equal to x minus c, not plus, x minus c. Next is control flow. Control data flow graph or diagram model. So this data flow graph model is a data driven model, as we have seen, in which the execution is controlled by data and it does not involve any control operations, whereas control data flow graph model contains both data operations and control operations. So this control data flow graph uses data flow graph as element and conditional as decision makers. So this contains both data flow nodes and decision nodes, whereas the data flow graph that we have discussed earlier, it contains only data flow nodes. So let's take an example, that is if flag is equal to 1, then x is equal to a plus b, else y is equal to a minus b. So flag is equal to 1 is the condition. If flag is equal to 1, then x is equal to a plus b, else y is equal to a minus b. How we can implement it? Using this control data flow graph model. So as I've told you, the control node is represented by a diamond or block. So this is the control node. It is represented by diamond block, which is the decision making element in this flowchart based design. So if flag is equal to 1, if it is true, then a plus b will get added and we will get x. And if flag is not equal to a plus b, that if it is false, then y is equal to a minus b. So this is how we implemented it using this control data flow graph diagram. Next is state machine model. As you can see, next is state machine model. So this is my state machine model. It is used for modeling reactive or event driven embedded systems whose processing behavior are dependent on state transitions. So this embedded system used in the control and industrial applications are the examples of this state event driven or reactive embedded systems. So the examples that I've told is embedded systems that are used in control and industrial applications. So the state machine model describes the system behavior with states, events, actions and transitions. State is a representation of current situation. Event is an input to the state. The event acts as a stimuli for state transition, and transition is the movement from one state to another state, and action is an activity to be performed by the state machine. So a finite state machine model is one in which the system is described using a finite number of possible states. So let us see one example. Suppose the system requirements are captured as when the vehicle ignition is turned on and the seat belt is not fastened within 10 seconds of ignition on, the system generates an alarm signal for 5 seconds. And the second is alarm is turned off when the alarm time expires, or if the driver or passenger fastens the belt, or if the ignition switch is turned off, whichever happens first. So I'm going to implement this using this finite state machine model. So here you can see the states are alarm off, waiting and alarm on. So these will represent the states: alarm off, waiting and alarm on. And the events are ignition key on, ignition key off, timer expire, alarm timer expire, then seat belt on. So these are the events. So as I have told you that event acts as a stimuli for state transition. So I have told you that the states are these, and for state transition, what acts as a stimuli? These events acts as a stimuli. So what is happening here? As you can see, what is happening here, when the vehicle ignition is turned on, okay, when the vehicle ignition is turned on, so this ignition key on, and the seat belt is not fastened. If the seat belt is not fastened within 10 seconds of ignition on, the system generates an alarm signal for 5 seconds. So this alarm is on, and this is the waiting mode. That is, the alarm is on for 5 seconds. It will wait for 5 seconds, and then if the seat belt is not fastened within the 5 seconds of ignition, the system generates an alarm signal for 5 seconds. So again, this is the alarm. So again I am repeating what is happening. This ignition key on, this event, it triggers the 10-second timer and transitions the state from alarm off to the waiting state. And if a seat belt on or ignition key off event occurs during the wait state, then the state transitions into alarm off. But when the wait timer expires in the waiting state, the event timer expire is generated, and it transits the state to alarm on from the waiting state, and the alarm on state continues until a seat belt on or ignition key off event or alarm timer expire event, whichever occurs first. So this is how we have implemented this example using the state machine model. I'm ending this class here. We'll continue with the same topic in my next lecture also. Thank you.